Hello everyone, welcome back to the Network Masters. In today's Cisco VXLAN series, we are going to discuss two major things. First one is the limitation of the BGP EVPN, and second, how the VXLAN with multicast optimizes those limitations. Okay, so let's first discuss about the limitation of the BGP EVPN. So in BGP EVPN, where is the pencil? So in the BGP EVPN, every leaf switches share its host database, which is the EVPN database, with other leaf switches. That means instead of doing flooding like we did in the ingress replication, the leaf already knows the remote MAC and sends traffic as unicast. So yes, EVPN reduces flooding significantly, but it does not completely eliminate flooding. So let's understand where flooding still exists. So there are some scenarios like unknown unicast. So if I'll give an example, just a sec. So if I'll give an example of the unknown unicast, let me remove this one and then suppose host node sends traffic to the MAC address that it has never communicated before. Okay, and in this case it is the H3, and H3 has not created a GAR for leaf 2, so leaf 2 doesn't know about the location of the H2. So if leaf 2 doesn't know about the location of the H2, if leaf 2 doesn't have information about it, it will not share anything with the leaf 1 as well. So now when H1 sends the packet to H2, the packet will reach to the leaf 1. Leaf 1 will check its EVPN database, like do I have the information of the H2, and like we do not have that information. So what leaf 1 will does the flooding into the network. So and when the packet reaches to the host 3, it will reply, and that packet when once reached to the leaf 1 will install that information in its EVPN database, and from that onwards it will do the unicast routing. So in this case BGP EVPN doesn't eliminated flooding of traffic in the network, correct? So let's go back to the slides. All right, yeah, so let me remove this one. Second thing is the broadcasting protocol. So there are some protocols by design. There are some protocols that are that are using broadcast by design. For example, like DHCP, okay, or NetBIOS, or there are some certain VM discovery mechanism as well. Okay, so in this case, there is no specific destination host, so EVPN cannot convert it into the unicast. So the leaf must distribute this traffic to all the VTAPs belonging to that VNI. So again, in this case, like we have some flooding in the network, right? Third one is the multicast application. So some application intentionally use multicast traffic. EVPN does not convert those multicast traffic into the unicast automatically. So this traffic still needs to be distributed to multiple leaf switches. Okay, again, which is the case of the flooding. Last but not the least is head-end replication load. So even in BGP EVPN, when flooding is required, the leaf switches perform the head-end replication. That means if I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If there are like 10 remote VTAPs or 10 remote leaves, the leaf create 10 copies. So just suppose leaf 1. Leaf 1 will create 10 copies of the same VXLAN packet, and it will send these copies to all the leaves. Okay, so in large scale fabrics, this can increase the CPU and processing loads, which is totally not recommendable. Okay, all right. So here comes the multicast. So before proceeding with the multicast, important clarification is multicast does not completely solve those problems. Instead, it optimizes where replication happens. So I'll say EVPN focuses on reducing flooding, but multicast focuses on efficiently handling the flooding that still exists with BGP EVPN. All right. So let's talk about like how it works. So if I'll create a all right, let's not create a topology. Let's take a reference of that paint here. Okay, suppose let's first understand the concept with the example. Suppose we have VLAN 10, okay, and that VLAN 10 is mapped to the VNI ID 10 10 10, and VNI ID 10 10 10 is mapped to multicast group 224.10.10.10. So wherever VNID 10 10 10 exists in the fabric, those leaf switches will join the multicast group 224.10.10.10. Okay, so in this case, how would be the packet flow? Let's say host 1 sends an ARP request. Okay, the packet will reaches to the leaf 1. Leaf 1 does the encapsulation. Leaf 1 will does encapsulation it into the VXLAN. So now instead of sending multiple unicast copies, what Leaf 1 does, it sends one packet to the multicast group, that is 224.10.10.10. Okay, now the spine switches which are already running the PIM protocol already knows which leaf switches have joined this multicast group, which in our case it is leaf 2, leaf 3, correct? So the spine replicates the packet in its hardware and forward it only to the leaf 2 and leaf 3, which are the members of that VNI, correct? So what has changed now? Earlier in the EVPN head-end replication, Leaf 1 Leaf 1 was responsible for creating the multiple copies. But now in multicast, Leaf 1 sends only one copy to the multicast group, that is 224.10.10.10, and now the network core performs the replication. Okay. Second thing is now flooding is controlled. Flooding is controlled. Okay, which is another important advantage. So if just suppose if discovery happens in the VLAN 10, only leaf switches that have VNID 10 10 10 will receive it. So other VNIs are completely isolated. So flooding is now limited to only one broadcast domain, which is great. Correct. So now flooding is controlled. Now head-end application issue is resolved. Okay. There is one more question which I faced usually, is if PIM is replicating traffic, doesn't that consume CPU? If PIM is replicating the traffic here, doesn't it consume like CPU? So the simple answer is no. Why? See, PIM is control plane protocol. Control plane protocol. It does not replicate packets. It only builds the multicast forwarding tree. Okay, and the actual packet replication is done by the hardware ASIC of the spine switches. Okay, so replication moves from, I'll say, edge CPUs to core hardware. That is the key optimization, and this is how we remove the head-end replication. Okay, lastly, if I'll give you the summary, just a sec. Lastly, if I'll give you a summary with the EVPN, EVPN reduces flooding using control plane intelligence. Okay, so it still uses head-end replication when flooding is required, but it reduces flooding using its control plane intelligence. But with multicast, it optimizes flooding by shifting replication uh, from the edges to the network core. Okay, by using the by using the PIM, which uses its multicast tree. So reduces edge, which basically reduces edge device load. Okay, I hope this thing is clear to everyone. Now let's proceed with the lab. So if I'll take you here, so in order to create the lab, we firstly need to do the IP assignment on all the devices, okay, which we have already done in the first lecture. Second thing, we'll create an underlay network, and for our lab we are using the OSPF from very scratch, and we'll be using the OSPF in today's lab as well. Then we'll create the two VLANs, that is 10 and 20, and those two VLANs are mapped with the BNID 10 10 10 and 20 20 20. Okay, and these VNI ID are VNI ID will be mapped to the multicast group 224.10.10.10 and 224.20.20.20. Okay, so there are some commands. There are some verification commands for the multicasting, like show IP pim neighbor. It will give you the neighbor information. Show IP mroute. It will give you the information about the multicast tree and the receiver tree. Show IP pim RP. It will give you the information about the RP. And show MAC address table. Like it will give you the information about the MAC address table. So without further ado, let's see this in action with the lab. All right. So let me remove this and let's proceed with the lab.